Hello, good morning, good afternoon to all my classmates and respected Tina ma'ams. My name is Gaurav Sanchala, serial number 102 from second year computer department. And our topic is linear and bilinear transformation. And my teammates are Nikunj Rupawatia, serial number 100, Kaushik Kucha 48, Darshan Wala, serial number 129, Gaurav Sanchela, that's me, and Deep Katelia and Jigar Darji. Oh, sorry. And this PPT is we present under the guidance of Dr. Tina Trivedi. So before moving to our main topic, that is linear and bilinear transformation, let's first understand what is mapping or transformation. So to find the geometrical representation of the function of a complex variable, it requires a usual practice of Cartesian plotting. Here a curves here a curves to real function y equals to function of x. In a complex domain, the function w equals to function of z. That is, we write w as u plus iv and the z as x plus iy. So above equation involves the four variable that is u, v, x, and y. So four-dimensional region is required to plot the in Cartesian fashion, which is not possible. So we are using the complex planes. One variable z, which is equals to x plus iy, and the other four variable w equals to u plus iv. Since each point x and y in z plane, there corresponds to point u and v in w plane. So a curve C in a z plane is mapped into corresponding curve C dash in w plane by a function f of z, which defines the mapping or a transformation. So in simple word, the curve C in z plane is mapped into w plane as C dash. So now let's start with linear transformation or mapping. So a mapping of the form w equals to az plus b, where a and b are real or complex constant, is called as linear or transformation. Linear mapping or transformation. In other words, the combination of a translation, rotation, and magnification is called as the linear transformation. Now the translation. Now we know the translation w equals to z plus a, magnification equals to w equals to a into z, and the function of rotation is w equals to e raised to I theta into z. Now how three this transformation combine and gives this equation, that is w equals to az plus b. Now you will find the a plus b as here a plus a, z plus a plus b, and magnification is az. So here we you will as you can see the az is there, but rotation is not visible in this equation. So here the a is complex constant. So the polar form of complex variable is this r e raised to I theta. So now in the place of a we write r e raised to I theta. So now these three transformation are present. Now further part will be explained by Darshan Wala. So over to you, Darshan.
Thank you, Gaurav. Good afternoon, one and all present here. I am Darshanwala. My serial number is 129. Now let's see the example based on linear transformation. The first question is, consider the transformation W is equal to 1 plus I into Z plus 2 minus I, and determine the region in the W plane into which the rectangular region bounded by the lines x is equal to 0, y is equal to 0, x is equal to 1, and y is equal to 2 in the z plane is mapped. In this solution, first we plot a given four line in the Z plane is see in the right hand side of PPT. Now begin with the solution. Given transformation equation is W is equal to 1 plus I into Z plus 2 minus I. Now we put W is equal to U plus IV and Z is equal to X plus IY in above equation. So we get U plus IV is equal to 1 plus I into X plus IY plus 2 minus I. Now we solve uh, this and now we solve this and uh, so we get U plus IV is equal to X plus IY plus IX minus Y plus 2 minus I. Now we uh, and we further separate a real and imaginary part, then we get U plus IV is equal to X minus Y plus 2 plus I into X plus Y minus 1. Now we equate real and imaginary part. Then we get U is equal to X minus Y plus 2. Give it equation number 1. And V is equal to U plus X plus Y minus 1. Give it equation number 2. Now we add equation number 1 and 2. Uh, Now we add equation number 1 and 2. Then we get U plus V is equal to 2x plus 1. Give it equation number 3. Now subtract equation number 1 and 2. Then we get U minus V is equal to minus 2y plus 4. Give it equation number 4. Next slide please. Now we put x is equal to 0 and x is equal to 1 in equation number 3. So we get a two line, that is u plus v is equal to 1 and u plus v is equal to 3, and y is equal to 0 and y is equal to 2 is put in the equation number 4. So we get another two line, that is u minus v is equal to 3 and u minus v is equal to minus 1. Now we plot above 4 line in the W plane. So we get a rectangle. If we compare a graph, is if we compare a graph in plotted in a Z plane and a W plane, so we conclude here. So we verify the definition of a linear transformation. Next slide. Let's say another example. Determine the linear transformation that maps the rectangle z1 is equal to 0, z2 is equal to half, z3 is equal to I, z4 is equal to half plus I onto rectangle w1 is equal to I, w2 is equal to 2I, w3 is equal to minus 2I plus I, and w4 is equal to minus 2 plus 2I. Let's see the solution. Solution. Okay. Here, Z1, Z2, Z3, and Z4 are the vertex of a Z plane, and W1, W2, W3, and W4 are the vertex on the W plane. So first we find the coordinate of those this vertex. So how to find it? Let's see. First we compare Z1, Z2, Z3, and Z4 to with Z is equal to X plus IY. So we get uh, Z1 is equal to 0 comma 0, Z2 is equal to half comma 0, Z3 is equal to 0 comma 1, and Z4 is equal to half comma 1. Similarly, we compare W1, W2, W3, and W4 with W is equal to U plus IV. So we get W1 is equal to 0 comma 1, W2 is equal to 0 comma 2, and W3 is equal to minus 2 comma 1, and W4 is equal to minus 2 comma 2. Next slide. Now uh, Z1, Z2, Z3, and Z4 we plot on the Z plane, and W1, W2, W3, W4 are plot in a W plane. If we compare both Z plane and W plane, so uh, from the Z plane, how to in we get a rectangle, and W plane we get a horizontal rectangle. So how to get its image? If we compare both planes, so I see, so we see that first of all rectangle is rotated by 90 degree. So in the rotation equation, that is W is equal to e raised to I theta into Z, we put theta is equal to pi by 2. And uh, if we see, if we see rectangle in a Z plane, lower edge is half, and if we see a longer edge of a rectangle in a Z plane, that is one unit. But in a W plane, if we see a shorter edge of a rectangle, that is it is one, and if we see a longer edge, it is two. So we uh, its size is double. It means it's magnify by 2. So what magnify equation is W is equal to A into Z. So we put A equal to 2. So we get W is equal to 2 into e raised to I pi by 2 into Z. Now we see rectangle is translated above x-axis. So we get it is translated by 1 unit. So so uh, here for a translation, the equation is W is equal to Z plus A. Here our Z is 2 into e raised to I pi by 2 into Z. But A is I. That is the final equation we get W is equal to 2 into e raised to I pi by 2 into Z plus I. Further explanation is explained by Deep. Over to you, Deep. Thank you.
Thank you, Darshan. Good afternoon to one and all present over here. Myself, Kateria Deep, serial number 40. As we have seen linear transformation or linear mapping, let's see linear transformation in vector space. So let vector u of f and v of f be the two vector spaces over the field f. Then mapping of u to v is called linear transformation or homomorphism of u into v. That is nothing but linear transformation, and it can be done if f of x plus y is equals to f of x plus f of y, and f of ax is equals to a into f of x, where xy belongs to u and f of x f of y belongs to v and a belongs to f. Or in other words, we can say that f of, when we combine both the formulas together, we will see that f of ax plus by is equals to a into f of x plus b into f of y. Now let's see some example based on linear transformation in vector space. So the question is given below as: check whether the vector set v is equals to xyz belongs to R cube, and the equation is 2x plus 3y cube minus 4z square is equals to 0 is a vector space or not. So let's see the solution. As we know, the V set has the equation that is 2x plus 3y cube minus 4z square is equals to 0. So we will take random coordinates, that is 2 comma 0 comma 1 and 8 comma 0 comma 2, which will satisfy the equation. That is, when we put the values, put the coordinates in the equation, it will give us the answer as 0. Now we will add the two coordinates, that is 2 comma 0 comma 1 and 8 comma 0 comma 2. By adding these coordinates, we will get a new coordinate, that is 10, 0, 3. Now we will substitute this coordinate in set B equation. Therefore, after substituting, we get the answer as minus 16. That is not equals to 0. Therefore, 10, 0, 3 coordinate does not belongs to V, and set V is not a vector space. Next slide, please. Let's see another example if a mapping is linear or not. So the question is given as, show that mapping of f is to V3R to V2R is defined as f of ABC is equals to C comma A plus B is linear. So let's see the solution. Let alpha is equals to A1 B1 C1 and beta is equals to A2 B2 C2 be any two elements of V3R and A comma B belongs to F. Now we know that f of A alpha plus B beta is equals to f of A alpha plus B beta. Now we will substituting the value of alpha and beta in the equation. So after substituting, we will multiply A inside and B inside the equation. After multiplying, we get f is equals to AA1, AB1, AC1 plus BA2, BB2 and BC2. Now we will open the brackets and add the elements. So f of AA1 plus BB2, comma AB1 plus BB2, comma AC1 plus BC2. Then, according to the question, we get the f of ABC is equals to C, comma A plus B. So that's why AC1 plus BC2 belongs to A, AA1, BA2 belongs to B, and AB1 plus BB2 belongs to C. Therefore, AC1, comma AA1 plus AB1 is a one bracket plus BC2, comma BA2 plus BB2 is a second bracket. Therefore, it satisfies the equation of the question, that is in the form of C comma A plus B. Now removing A from the first bracket, we will get A bracket open C1 comma A1 plus B1 plus B bracket C2 comma A2 plus B2. Now according to the question, we know that C comma A plus B belongs to f of ABC. Therefore, we will rewrite as A into f of A1 B1 C1 plus B into f of A2 B2 C2. Then we will satisfy that we will know that f of A alpha plus B beta is equals to A into F alpha plus B into F beta. Hence mapping of F is linear. Now the bilinear part will be explained by the Kaushik. Over to you, Kaushik.
Thank you, Deep, for your explanation. Myself, Kaushik Kucha, serial number 48, would like to evaluate the concept bilinear transformation or Mobius transformation. A transformation of the type W is equal to AZ plus B divided by CZ plus D, where A, B, C, and D are real or complex constant such that AD minus BC not equal to 0 is called a bilinear transformation. Mobius transformations are projective transformation of complex projective lines. They form a group S group, which is projective linear group. Bilinear transformation is a special case of conformal mapping called Mobius transformation, used to convert transfer function of linear time variant filter in continuous domain to a transfer function of linear shift invariant filter in discrete time. As it was first studied by August Ferdinand Mobius, so it is called as Mobius transformation, which is also known as Tustin's method. Next slide. Now, another important part of Mobius transformation is cross ratio. So, coming towards its definition, if W1, W2, W3, and W4 are points in extended complex plane and its cross ratio is denoted by W1, W2, W3, W4, then it is defined as W1 minus W2 into W3 minus W4 divided by W2 minus W3 into W4 minus W1. The theorem proves that if there are 4 points Z1, Z2, Z3 and Z4 in the Z plane and corresponding images in W plane are W1, W2, W3 and W4 under a bilinear transformation, then their cross ratios are equal. That is, this theorem cross ratio are invariant under bilinear transformation. Another useful result that will be used to solve examples is given below, which says that If 3 points of Z plane are given and also corresponding points of W plane are given, then the associated bilinear transformation can be found using this formula: Z minus Z1 into Z2 minus Z3 divided by Z1 minus Z2 into Z3 minus Z, which will be equal to W minus W1 into W2 minus W3 upon W1 minus W2 into W3 minus W. This is a useful result which will be used to further solve examples. So examples will be explained by Jigar. Over to you, Jigar.
Thank you, Kaushik. Good afternoon, ma'am. Good afternoon, sir, and my dear friends. I am representing the slide of the example based on bilinear transformation. So here's the first question. Find the bilinear transformation which maps points z equals to 2, comma 1, comma 0 onto the points w equals to 1, comma 0, comma I. So we have the values z1 equals to 2, z2 equals to 1, z3 equals to 0, and w1 equals to 1, w2 equals to 0, and w3 equals to I. So as we know the cross ratio formula, which was explained by Kaushik Gupta in the previous slide, z minus z1 into z2 minus z3 divided by z1 minus z2 into z3 minus z equals to w minus w1 into w2 minus w3 divided by w1 minus w2 into w3 minus w. So by putting the values of z1, z2, z3 and w1, w2, w3 on the further step, z minus 2 into 1 minus 0 divided by z minus 1 into 0 minus z equals to w1 minus 1 into 0 minus I divided by 1 minus 0 into I minus w. So z minus 2 divided by minus z equals to minus I into w minus 1 divided by I minus w. So we will take the minus I on the left hand side of the denominator. So we get z minus 2 divided by minus z equals to w minus 1 divided by w minus I. So by solving both the equations, we by applying component or dividendo, that is numerator plus denominator divided by numerator minus denominator, we get z minus 2 minus iz divided by z minus 2 plus iz equals to w minus 1 plus w minus I divided by w minus 1 minus w plus I. So by solving this equation, we get, next slide, z minus 2 minus iz divided by z minus 2 plus iz equals to w minus 1 plus w minus I divided by I minus 1. So by solving the equation, z minus 2 minus iz into bracket I minus 1 divided by z minus 2 plus iz equals to 2w minus in bracket 1 plus I. So by multiplying minus z into the bracket, we get zi minus 2I plus z minus z plus 2 plus iz divided by z minus 2 plus iz equals to 2w minus in bracket 1 plus I. So zi plus zi equals to 2iz, my plus z and minus z will get cancelled out. Minus 2I plus 2 divided by z minus 2 plus iz plus 1 plus I equals to 2w. So 2iz minus 2I plus 2 plus 2 minus 2 plus iz plus 2y minus 2 divided by z minus 2 plus iz equals to 2w. So we'll get 4iz minus 4I divided by z minus 2 plus iz equals to 2w. Therefore, in the final solution, we'll get 2 common on both the sides. So w equals to 2iz minus 2I divided by z minus 2 plus iz. So here's the solution, and now we'll move on to the next sum. Next slide. Find the bilinear transformation of z equals to 1 comma I comma minus 1 and w equals to 0 comma 1 comma infinity. So we have z1 equals, can we skip this question? कौन सा मैम, ये वाला?
Because ये हो गया ना, so can we
हाँ
skip this question and we will move forward? Yes.
हाँ. So the next sum will be explained by my friend Nikunj Rupawade.
Nikunj, we can't hear you. Are you there? निकुंज है मीटिंग में? अच्छा, लेफ्ट हो गया.
हाँ मैम, एक सेकंड वहाँ.
हाँ, okay, fine, okay, no problem.
Hello.
हाँ निकुंज, हाँ, we can hear you now. हाँ.
So thank you, Jigar. Myself, Nikunj Rupavatia. Now I will be explaining the further sum, that is to show that the transformation W is equal to 2z plus 3 upon z minus 4 maps the circle x square plus y square minus 4x is equal to 0 into the straight line, that is 4u plus 3 is equal to 0. So here in the question we have given the circle equation, that is x square plus y square minus 4x is equal to 0. So from this equation we are going to get the center, that is 2 comma 0, and the radius, that is equal to 2. From the center we as you know that the center equation in the complex form is x plus iy, that is c is equal to 2. Now further proceeding with the complex equation of the circle in the complex form, that is z under the modulus z minus c is equal to r. So by putting the values, that is it becomes the z minus 2 is equal to 2. Now we have given the w is equal to 2z plus 3 upon z minus 4. Now converting this equation into the form of w, that is z is equal to 4w plus 3 upon w minus 2. Now putting this equation, that is equation number 2 in 1, we get 4 inside the mod 4w plus 3 upon w minus 2 minus 2 is equal to 2. Doing the cross multiplication, further we get the 4w plus 3 minus 2w plus 4 upon w minus 2 is equal to 2. So it becomes 2w plus 7 upon w minus 2 is equal to 2. Taking w minus on the left hand side, right hand side, it becomes under the mod 2w plus 7 is equal to 2 into under mod w minus 2. Now further we are squaring on both sides, that is mod of 2w plus 7 the whole square is equal to 4 into w minus 2 the whole square. Here a small concept is that the mod of z square is equal to 1 and also z into z bar is equal to 1. So converting this z into z bar, so it becomes 2w plus z 7 into 2w bar plus 7 is equal to 4 into w minus 2 into w bar minus 2. So further doing multiplication, so it becomes 4w bar plus 14w w plus w bar plus 49 minus 4w bar plus 8 into w plus w bar minus 16 is equal to 0. So here the 4w bar and minus 4w bar w bar is getting cancelled, and further the equation, it becomes 22 into w plus w bar plus 33 is equal to 0. Here this equation is getting divided by 12. So dividing it by 12, it becomes 2 into w plus w bar plus 3 is equal to 0. Here we are putting the w plus w bar, the value of w plus w bar, that is w is equal to u plus iv, and w plus w bar is equal to u minus iv. Adding these two equation, it gives you 2u, and putting this value 2u in the equation, it becomes the 4u plus 3 is equal to 0. Hence, with the help of the transformation, we have converted the circle there into the straight line. Next slide. Let's take the another sum based on the bilinear transformation. That is, so that the transformation w is equal to I into 1 minus z upon 1 plus z transform the circle, that is under mod z is equal to 1 into the real axis of w plane, and the interior of the circle, that is mod z less than 1 into the upper half of w plane. Here we have it is given the mod z is equal to 1 and mod z less than 1. Combining these two, we get the mod z less than equals to 1. Now here also we have given the transformation, that is w is equal to I into 1 minus z upon 1 plus z. Converting this whole transformation into the form of w, that is z is equal to minus of w minus I upon w plus I. Now we are squaring the equation number 1, that is mod z the whole square less than equals to 1. As we have seen previously that the mod z square is converted into the z bar, here also it implies z. So
By now putting the values of the z and the z bar, we get minus w minus I upon w plus I into minus of w bar minus I upon w bar minus I less than equal to 1. Cancelling this minus sign, we get w minus I upon w plus I, w bar minus plus I upon w bar minus I less than equals to 1. So now we are doing the cross multiplication. So we get the equation as the WW bar plus WI minus W bar I minus I square less than equal to WW bar minus WI plus W bar I minus I square. Here the WW bar and I square is getting cancelled on both the sides. So the equation becomes 2I into W minus W bar less than equals to 0. So here also we are putting the value of the W minus W bar, that is 2IV. So by putting this value, we get the minus 4V less than equal to 0. Converting into simpler form, that is 4V greater than equal to 0. Now we have to, now the Z, we have seen that mod Z is equal to 1, that is given. So putting the value of the Z, that is 4V is equal to 0, that is V is equal to 0. It means in the graph that is real axis of the W plane, and also Z is less than 1, that implies 4V greater than 0, that is the upper half of the W plane, hence it is proved. So now I hand it over the applications of the linear and bilinear mapping to Kaushik Kucham.
Thank you, Jigar and Nikunj, for the explanation of examples. Coming towards application parts, application of linear and bilinear mapping is used in IIR filters. So what is IIR filter? The infinite impulse response filter is a recursive filter in that output from the filter is computed by using current and previous inputs. And because the filter uses previous values of the output, there is a feedback of the output in the filter structure. An IIR filter is an infinite impulse response. It's one of two primary types of filters used in audio and digital signal processing. The other type is FIR, finite impulse response filter. Coming towards some more examples, the most common is that graphical operations are represented by linear transformation. The mouse icon moving on our desktop while moving the mouse also requires linear transformation. Digital filters designed via bilinear transformations are guaranteed to be a stable ones. Use of bilinear transformation S is equal to Z plus 1 divided by Z minus 1 is suggested as an alternative to log root locus method for plotting root loci, which cannot be accommodated satisfactorily on linear scales. Familiar rules for locus construction are applicable in the Z-plane also. One of the major applications of bilinear transformation is in audio signal processing, which uses bilinear transformations to transform the signals. Now to revise, I like to invite Gaurav to conclude our PPT. Over to you, Gaurav.
So it's time to conclude our PPT. So what we have learned in the PPT. So firstly, we have seen the meaning of transformation. So in Z plane to W plane, we are converting the Z plane into W plane. Then we have seen the definition of linear transformation and sums on that. So equation of linear transformation is W equals to ZA in plus B. And then we have seen the linear transformation in vector space and sums on that. So these are these two condition, and the combined condition is this. And then we have seen the definition of bilinear transformation and sums on that. So equation of bilinear transformation is this. And after that, at the end, we have seen the application of linear and bilinear transformation. So that's it. And thank you.